Okay, so today I want to consider in a little more depth the notion of internal set. Because it is interesting that in non-standard analysis not all sets are so equally legitimate. So there are sets which are internal, which are legitimate, and other sets which are less legitimate. Yeah? And we found already examples of set. Say the set star n is a legitimate set, so it is called internal. And the set n, which is a subset of this set star n, was found to be, let me consider to be clear the set star n minus n. So this set somehow is illegitimate, so we call it external. So what is the difference? The difference is that the set star n is it is object. It is not only collection of some elements in our non-standard universe, but it is itself an object. So sets are also objects, yeah? Not only. And this, it turns out that it is not such object. So why? So it is a set of infinite non-standard numbers. Now we know that for standard integers we have the following principle, that for any set A subset in N, it is what is in the standard universe. There exists, say, A in A, such that A is the minimal element of A. No, here what I write here is the shortcut for the following. A is the minimal element of A. Let me put it in brackets. It is this same that for all B in A, B more or equal than A, and C in A C for any C in A, if C less than A, implies that there exists element Z in A such that D more than C. Yeah. So this says that A is less or equal than any other element of the set A capital, and this says that if you take any other element of A, which is if you take other number is n. If you take any C is n which is less than A, then there exists D such that D more than C. So the second line says that this A is the smallest. So the first line says that A is upper bound of the set A capital, and the second line says that it is the smallest upper bound. If you take any other number which is smaller than A, that's some number of our set yes, if you take smaller than A, then just a minute, it is minimal, no, for OB, and there for any C that less than it is the greatest lower. So this said that A small is the lower bound of A, and the second says that
wouldn't be
just a minute, we are looking for the lower bound. So this says, the first says that A is small is lower bound, and the second should say that it is the smallest, the greatest lower bound. So if you have some C which are more than A, then there is this D which is greater than C. So any smaller C is not lower, any larger C is not a lower bound. Yeah.
I'm not exactly sure why would we need the second line. Shouldn't it be sufficient, the first line and the fact that A is an element, the small a is an element of big A?
No, the first line says that A is less or equal than all elements of our set. Yes, and the second line says that it is the largest such element.
But
there is no,
like, isn't the second line like trivial because of the fact that A is an element?
so if we assume that if you take any other number which is smaller, then there will be some elements of our set which are larger than the C. What is wrong here?
The decision it's not really bad. It's just the fact that it seems that the second line.
This is our set A. No, this is our set A. We find element A small. such that this element is smaller or equal than all other elements of A. Yes? And if you take any element C here, then there will be inevitably some element here, D, which will be less than C. D is less than C. Yes. You meant this, yeah?
Yeah.
Yeah, so this is, so A is the greatest lower bound of A capital. Greatest lower bound. And the main principle, such A exists universally, but it exists that A is element of A. So a set A capital, A capital was arbitrary subset of arbitrary set of natural numbers, has a minimal element. Yeah. So it is written here for any A there exists A such as A is minimal element of A capital. Yeah. And the shortcut. Now, by transfer, if A is a subset of star n, is internal set, then the following is true. There exists A in A, A is the minimal element of A. So here let me write too much here. It is any A okay, so if A is a A is a internal set, then this is true. But for if A is star n minus n, for example, so it is a set of infinite integer numbers. What happens? A cannot have minimal element. A has no minimal element. No, why? Otherwise, if it has, if A in N, then say A plus 1 also in N. Yeah? So we found larger, just a minute, so we found the smallest element, A minus 1, also in N. Just a minute. If A is N, so if A is finite, then A does not belong to A. And if A is star N minus N, so it is infinite, then A minus 1 is also infinite, also is infinite. No, this means that A is not minimal. So there is no smallest minimal element. No, similarly, the set of finite integers also is not internal, because if you consider the largest of them, it is bounded from above by some infinite number, and we know that any bounded set of integers has a maximal element. But this maximal element, if it is finite, then the next A plus 1 is also finite, so it's not maximal. If it is infinite, it is not in our set. Yeah? So something is wrong. And what is wrong? This set, star N minus N, is not internal. It is not an object of our universe. And it is important to find the ways how to prove that a certain set is internal, or to construct these sets. Yes? In the set theory, we have some series of axioms which show us how we can start from some set and construct more complicated sets. Yes, and here we should have the same. Situation. So let me start from definition. A set A is called definable. Definable, say, in our universe, in the standard universe, if A equals the set of some x, it cannot be left bare, it should be, so our universe U is a union of different levels. So it should be at some level, say un, for some n, such that, say, alpha of x. So these elements should satisfy some condition. There is some formula. This formula can contain some parameters or some constants. Constants should be taken from this universe U. Alpha is a formula. Constants from U. No, the formula can be different. It can be, say, x equal x. It is a formula. No parameters, and it is true for any element x. So it can be not very informative. No, the same similar definition for a set definable in start view. Now here we have to take constants from star u, and it is not in un but in star un. So this is a definable set. No, in fact, it is not so informative, because this formula can be alpha x is element of some set, given set. So again, we return to all sets of our universe. But more informative is the formula A is the set of x b in A such that holds true alpha of x. So we, from the beginning, consider a subset of a given set A. So we take the general set and then impose some conditions. It is sort of more informative. And then the theory which I mean here is the following. Suppose A is an internal set. Then B equals the set of x in A alpha x is also internal. It is already interesting because, as I said, alpha of x is arbitrary predicate, arbitrary property, but nonetheless we have this quite general theory. Now let me explain you why it is true. what does it mean that A is internal set? A is internal set if the following, we have to return to our definitions, to our model. We have there exists a function f from I to we had our standard universe U to U number n and more than 0, so it should be sets such that f of I is a set almost everywhere. So our, so to say, set is in fact this function with values in sets. And its, so to say, elements are the samples. For any I, we take sample of this set, so one element. Yeah. Now, there is set I. Now, what is parameters? Let C1, C2, and so on, some Ck be parameters of the predicate parameter constants. Predicate alpha. Yeah, there are also C1, Ck are elements of star U, so they are also the functions. Cp equals a function Cp of I. Equal 1. Okay. So each of them is a sequence or this family of such elements, and Cp of I are elements of U. No, again, almost everywhere. Yes? So this we have parameters. And now, what does it mean that it holds alpha of S? We have again to see what does it mean. So element A in B. What does it mean that element A in B? First of all, A equals some function f. Yes. From I to U. And A is element of B if and only if we have the following thing. There exists, there is true alpha of f of I, C1 of I, and so on, Ck of I, almost everywhere, for almost all I. Yeah? No, okay. Now we are almost ready. Let us define for any I almost all I, define a set. So we have A, B, C, D of I. The set of A not A small, it's A capital. And A small A small is the function fg of I. Yes? So A capital is realized by the function f of I. Yes? And A small function g of I. So G, A, B, C, D, E, F, G, H, such that it holds alpha of H, C1 of I, H, H in f of I, such that it holds alpha H, C1 of I, and so on, Ck of I. Yeah. So for be done by for almost all I. So for almost all I, we for these i's. So what does it mean? For each I, or almost each I, we have some values of this, so to say, constant, C1 of I, and so on, Cn of I. And we have all possible elements of A, elements of f of I. And let us speak of them such that they satisfy this condition alpha with this age, with these parameters. Yes? As soon as we do it, we have a set which I call D of I. Yeah? And so we have at last a sequence D of I, it is a sequence of sets. Yes? And by definition, such a sequence is itself an element of star U. Yeah? It is an element of star U which we call a set. Yes? And so the set B is this function D of I. in I capital. No, again, it is defined almost everywhere. So this way we found an object which is what we need. So we defined a set as element of our universe star U. It is a consequence of our way how we define these elements of star U. Element of star U, even if it is a set, is also element of star U, is always equivalence class of sequences, or of the generalized sequences. So the point is that if you have this predicate alpha, so it is some condition, it is applied and tested element-wise for any I. So this is how the model is constructed. So this way we found, proved this great theorem. No, in particular, if A is element of star U, this means that A is an internal set. And B in A subset is a definable set, then B is internal. So definable subset of internal set is internal. No, for example, yeah.
Would one be able to prove that theorem just using the transfer principle? And if, would it be possible, I'm not sure, but would it be possible to prove that with trying to apply transfers?
You know what? In fact, what I'm telling you now is some fragment of proving the transfer principle. Yes, this reasoning which I used here was more or less exactly transfer principle. So I did not prove transfer principle because it's dull, but here it can be regarded as a particular case of transfer principle. Of course, you are right. No, in fact, here we have B is A intersection with B in this case. Yes, if B is from the beginning set a subset of A, so it more or less repeats the previous theorem. Yeah. No, now I want to prove what I did not prove last time. We proved that the set of infinite numbers, integer numbers, is external. But what about finite? No, I already gave some reasoning, but here I can give it more shortly. Theorem, it is that n is not internal. The set of standard integers is not internal. So why? Suppose n is internal. Then star n is internal. We know that star n is internal. So this let us define n by the following formula. So n equals star n minus n equals the set of, say, x in star n, such that its elements are not in n. It is not negation. It is not true that x is in n. Yeah? So this is definition. By the previous theorems, I mean main theorem, that this is a definition of subset of internal set is defined by this formula, and this formula contains a parameter n. And we decided that n is internal. Suppose n is internal. Yes. Then by the previous theorem, star n minus n should be internal. But it is not. Hence, n is external. So we said n external. No, okay. Just a minute. Let's go further, because we are talking about the sets, but especially important sets are functions. So next goes internal and external functions. So next theorem. If A, B are internal sets, then the Cartesian product is internal. Yes, now we have to again return to definition what is Cartesian product of two sets which are elements of star u. Elements of star u. So A is the same as F is the set F of I. Yes, for F of I is a set element of U for almost all indices I. Yeah. B simply is a set of it is a G of I. G of I again is a set. And A, B, this was a theorem which I proved before, is the following set H of I, which is equal to F of I cross G of I, also almost everywhere. So it is a more or less definition, yes, or what I called it semantics, but no, it is and the theorem was that if you consider it materially, so A is this thing, where is a set here? You have to consider a set, M, F. It is a set, yeah? And Mg is also a set. It is the set of all functions such that the value of this function at almost every d is contained as an element of correspondingly f and g. Yes? So these are two true sets. Yes? And it was the theorem that product of this equals simply m h. Yeah? And here we have to return again to the basics, and we have to recall that the Cartesian product is the set of ordered pairs. Ordered pair is in fact a set theoretical pair of two elements, say f, and the second is a pair of fg. Yes, and then analyze what is all means, and then we have this result. So I already did it, so let us believe that it is true. Yes? So this way we again reproduced A cross B as also element. So here we have all the time the same trick that we jump from these sequences to sets of corresponding functions. Yes, and use the property of ultrafilter that for any subset of ultrafilter, if either this subset or its complement are elements of ultrafilter, for any subset of index set. Yeah, so yes. Now the next theorem is the theorem about the functions. So consider the function. we have, let me write, internal functions. So consider two sets A and B are sets in star U. So two sets in our non-standard universe, and consider F from A to B. So what is F? So for in fact, how to define F? We have to consider A cross B, and F is a subset here. F is a subset of A cross B. No, in some cases this. Subset such that for any A, for any A in A, there exists unique B in B such that the pair AB belongs to F. Yeah, this is the definition. So, yeah. Now, F is a set. Yes, no, set in the naive sense. It is a set. And some sets are internal, which are legitimate elements of star U, and some are not. Yeah? And now corresponding theorem. The following theorem. Suppose we have this set F A and B, and AB internal and F of A for any A in A capital, F of A is the following. We have to, there exists a term formula in our usual sense, term mu of A. The term is logical thing. We have rules how to interpret term. Each term has its interpretation. In the universe star U. So suppose this F is not arbitrary, it's given by some term, where mu is a term in star U. Then F is internal. No, the proof is shorter than the formulation of the theory. So what is F? It is the set of C in U, star U, at some level n, such that the following is true. There exists S in A, there exists Y in B, C equals pair XY, and Y equals mu of X. Simply so. So the set F is defined by this. So this is this term which was here in definition. So we should have some formula. Yes, we don't use, so here we say goodbye to all the notional function which starts from, I think, Dirichlet. That function is arbitrary relation or mapping and so on. No, it should be a formula. Then the further goes. But this formula, of course, can contain, say, a lot of non-standard parameters or constants. So we have a great freedom, but not arbitrary freedom. So F, first of all, it is nth floor of star U is itself internal set. And second, this is a definition. It is all long predicate. Yes? So we are in the framework of the theorem. F is an internal set by the theorem. Yes, and to show you something interesting, let us consider immediate application of this, some funny theorems. It's called overspill and underspill. Yes. So if you put a mug under and try to pour beer there, then one of two happens. Either this beer goes over the board, it's called overspill, or it is not enough beer, it could be a little more, it's called underspill. So this is a funny phenomenon which happens here. Suppose we have, if you have internal function, no, in particular it can be internal sequence. So, now sequence, how it's Sn. Here n in star n and Sn in star r for all n. So it is a sequence where the indices n are already non-standard integers and the values are non-standard reals. So this is a sequence. And this, as any function, can be internal and external. So suppose Sn is an internal sequence. Suppose for some n in R plus, so just ordinary positive number, and for all standard n, the following holds. Module Sn less than n. Then there exists an say nu in star n minus n, so infinite number, such that module Sn less than or equal than n for all less or equal than mu. So this means that if you have a sequence which is bounded, yes, and it is internal, then this fact of boundedness continues somehow beyond the bounded integers. Yes, so here we have n. Yes, here we have star n, and this sequence is bounded here. Yes, by this m, and it continues to be bounded some farther, and this is new, maybe to universally for all of them. Yes, so here you see. No, you could say, but how? Say we can define a sequence which is 1 for all Sn is 1 if n is finite, and 0 and say 2 for n infinite, or maybe some infinite number for n infinite. Yeah, just define it by hand. So okay, this definition is wrong. Because the sequence is not internal. Yes, why it's not internal? Because it uses not internal notion of a set of finite numbers. This predicate being finite is not internal. Yes. No. Okay. So how it is proved? Let's consider the set A, the set n star n, such that module Sn more than n. Yeah. So this set first of all, it is subset of some internal set. And second, it these sets consists of elements which satisfy this condition, which is surely a predicate with a parameter which is within our universe. This means that A is internal. And for internal sets, we can use the transfer principle. A contains the smallest element nu. Have any set, subset of n without star, it has minimal element. Yeah? This set is internal, so this also true. Yeah. Contains minimal smallest element nu. Nu cannot be finite. Yeah, because if it is finite, so for some finite n equals this finite nu, we have that as n more than n. So nu is infinite. Or maybe I say A is an empty set. It also can happen. So if this sequence is bounded by n for all non-standard n, then this set is empty. This set A. This set A. Okay. So we have this thing. Other theory which also is used is suppose Sn is an internal sequence. And the following is true. S n are infinitesimal for all standard n. So here I use two external things. First, being infinitesimal, it is external, and n is also external. Yeah. So suppose then there exists nu in star n minus n, so infinite nu, such that Sn are infinitesimal for all n less than nu. So again, this property being infinitesimal spreads beyond the finite indices. Yeah. No, again, this theorem does not require long proof. So let us consider the following sequence. Consider the sequence Cn equals n times Sn. Just multiply it by n. Yes? There is a small another reason which I skip, that the sequence Tn is internal. It's internal if Sn is internal. So this multiplying by t is internal. So the property of t being of this form is internal, which is a formula. So we have an internal sequence. And by the previous Tn for all n in so this Tn, if it was infinitesimal, then multiplying by n leaves it infinitesimal. Yeah? So we have the sequence Tn, which is infinitesimal. Now this is a bad condition, but we can write it the following thing: Tn less than 1 for all. If it is infinitesimal, no, it is less than 1. And this is already internal condition. So if it is internal condition, then there exists a nu star n minus n such that model Tn less than 1 for all n less than mu. So by the previous theorem, we can spread this boundedness of Tn. Now let's return Sn equals Tn divided by n. Now we know that Sn is infinitesimal for standard n. For Sn is infinitesimal. For minus n and n less than mu, we have the following thing. Sn is Tn is less than 1 and n is infinite. So this fraction is also infinitesimal. Sn, model Sn is less than 1 over n is infinitesimal. Yeah? So we have two parts, and in both is infinitesimal by different reasons. Yeah? So this means that this property of being infinitesimal also spreads, but it spreads only for internal sequences. Yeah. And now I reach finally one moment. Okay. Now comes this promised overspill, and it was already overspill, but another promise, another thing. Suppose Sn is internal decreasing. Let A is some number, also non-standard number. Then the property Sn less than A or more than A hold for a finite set of n, sorry, just in the beginning, which can be called under spill. Or for all n less than mu, mu is infinite, or for all n in start n. No, the last two things are called overspill. Yeah. So it's another variation on the theme of internal sets. No proof. I define A is the set of n is star n such that Sn less than A, less or equal than A. Again, this is internal set. A is internal. So it has a minimal element A, or other possibility A is empty. It's also possible. So it decreases, but say if all the terms are positive and A is negative, then we set it. No. This minimal element, if A is finite, no, if A is finite, the set is finite. Sn more than A for a finite set of n. If nu A is infinite, A star n minus n, then we have overspill. This means Sn more than A. Not nu. if nu for all n less than nu. If A is empty, then as n more than A for all star n. Yeah, so you see, it is impossible to somehow define in human terms what is finite or infinite. Yeah, it is, I would say, independent quality, so we can introduce independent, say, predicate to distinguish finite or infinite. But in the non-standard analysis as it is, this property does not exist. Yes, contrary to our feelings. Okay, so let us finish today. And we have a long break. No long break, it again consumes 2 lectures, no? Okay, let us see you after.
Thank you.
Yeah.